Am I audible?
Yes.
Okay. So you can start. Let me see how the screen falls. Okay. So I think it's visible, right? Screen is visible or
Yes.
some comment is there okay, only. Okay, you have doubts, so you can ask me that first. Let me check. Uh, three questions. Question three in assignment nine. Okay, once let me check the question. Question. We can download the PDF. Question for a diatomic gas, the constant molar volume heat capacity. Okay, let me check. Um, Let me just yes.
The answer is given incorrect, I think.
Okay, what is your answer?
7 by 2 r.
So, like toward here it is given as 3R. So for diatomic gas, the constant molar volume heat capacity at extremely high temperature. So why it is 7 by 2R?
3 plus 2, 5. 3 for translational, 2 for rotational. And
Yes.
this is 5 by 2 r and 1 vibrational full contribution, full r.
Extremely high
But where the
temperature.
temperature is very high now,
Yes, the temperature is very high.
it will-
So when the
and that
temperature,
atom will be separated.
yes, yes, repeat it. No, so you are considering the dissociation. So in that case, the diatomic molecule, the gas, the molecule will be become two monoatomic molecule. You want to say, right? The molecule will be dissociated, right? Otherwise, when it will be three by. Okay, let me calculate.
Yes,
Okay, so I understand the
yes.
question. Let me share the screen now. Uh, I'm sharing the screen. Let me connect it. Then so, let me connect it again. So, okay, so it is a diatomic gas. So let's say we can consider H2. H2 is a diatomic gas, right? Now there would be translational motion, which contribute 3 by 3 into
3
half
by 2 r.
kVt. Each mode contributes half kVt and there is a 3 degrees of freedom for translational mode. So it is eventually 3 by 2 kVt. Now coming to rotational,
2 into half kVt.
yes, because it's the Linear molecule, because diatomic means always it will be linear. So it will be 2 into half kBt. So it is essentially kBt. And it's vibrational,
1 into kBt.
3n minus 5. Here n is a 2. So 6 minus 5 is 1. So 1 mode will be there and it's kBt. It's kBt even. Yes. So overall energy will be 3 by 2 plus 1 plus 1 kBt. So eventually it will be 7 by 2. Yes, 7 by 2 kBt will be the right answer. Probably answer is given wrong. Okay. Here is no
And
twist.
what about the separation?
That dissociation.
Yes.
No, you can't consider the dissociation. If the dissociation is occurring, then obviously you have to consider monoatomic gas. So when you are considering a particular gas and you are calculating any heat capacity, CV, Cv, anything else, so in that case, you can't consider any chemical reaction or any physical dissociation, that you can't consider. Okay. So while calculating this, you have to fix that is a diatomic molecule. Okay. Uh, when the things become important in the low temperature, because in high temperature means extremely high temperature means they want to say that the temperature is way greater than theta V and theta R. So when theta V and theta R both are less than the T, so both every mode will be important, right? So that you have to consider. When the temperature is, let's say that I have already discussed, if temperature is less than theta V, then you can't you have to ignore the vibrational degrees of freedom because that will contribute zero in the energy. Uh, if it is theta r also less than theta r, then only translational mode will be contributing. Other every rotational vibrational, each and every mode will be zero. Contribution from that mode will be zero. So yeah, it is obviously 7 by 2 kBt. Okay. So is there any other doubt regarding any question? I did not gone through this assignment question this week. If you have any doubt, so because it's the second last class, in next class there is nothing else to discuss, nothing new, because today I will discuss the Maxwell Boltzmann and Fermi Dirac that is already covered in this week. That part I will discuss totally. After that, there are further few things, but I don't think that should be discussed. That is little beyond. Only the density operator, I said you that I will discuss that. So that will take sometimes 15 to 20 minutes that I will discuss in last class. And you other doubts, you have to collect the all doubts from the assignments given the already given the assignment and the upcoming assignment from anywhere, any course, even from TA, that you have to collect the doubts and you have to ask. Okay, so that you have to do in the next class because in next class I
Okay.
don't have lots of content. Okay, so let's see today how much I can complete. Okay, so today we'll discuss the Maxwell Boltzmann, Fermi Dirac, and Bose-Einstein statistics. We discuss some in a vague way. In surface level we have discussed, but in details we did not discuss. I thought that it will not be taught in the course, but in this week I we saw that sir already discussed something. So uh, okay, if you have any, oh yes, yes, any, or you can WhatsApp me, not only email. You can WhatsApp me. I am writing my WhatsApp number here, so you can directly WhatsApp me. So this is my WhatsApp number. So if you have any doubt or any other query regarding notes, books, so you can ask me that also. Okay, this is my WhatsApp number. Okay. Okay, so now I am again sharing the screen is sharing and I have to connect it. Then I will go next with it. Okay, first where is display. Okay, okay. So today we'll basically Okay. First, we have to understand that Bose-Einstein and Fermi-Dirac statistics. Maxwell-Boltzmann, we know that discuss the Maxwell-Boltzmann, Fermi-Dirac, Bose-Einstein. This is the short form. Okay. Maxwell-Boltzmann, Fermi-Dirac, and the Bose-Einstein statistics. So we know that for this thing should be clear because in this class it will be it may be confusing, but we know that for classical particle, any classical particle it may be, for classical particles they follow Maxwell Boltzmann distribution. Okay, this is MB set. Essentially it is called as MB set. Quantum mechanical particle, we have already discussed this. For quantum mechanical particles, if it is boson, then they will follow the Bose-Einstein distribution. First, I think it should be right. Okay. Bose-Einstein distribution, that is called B stat, or if it is fermion, then the particle will be called boson. When the quantum particle follows the B stat, it will be called as boson. And if it is following the Fermi-Dirac distribution, then it will be called, these things we have already discussed. It will be FD stat, then it will be called fermion. Okay. So, how you can understand that whether a particle will be boson or fermion? That we have argued like this: when a particle, now we will be talking about only quantum mechanical particle. Classical particle is clear, the Maxwell set, MB stat. In case of quantum mechanical particle, if the particle spin at full integral spin, like 0, 1, 2, like this, then it will be called boson. These things we have discussed again. I'm just repeating these things. Or if it is half integral, 3 by 2, 5 by 2. Obviously, it is plus minus. Plus minus I am not writing. 5 by 2. So then it will be called fermion. Essentially means the scheme is like this. Just understand it. If if a particle is spin is full integral, if the spin is full integral, then that particle should have the symmetry wave function. So essentially, when a particle has a symmetric wave function, because we are talking about quantum mechanical particle, and we know that for each and every quantum mechanical particle, a field wave function is associated. When a wave function is symmetric, then the spin will be full integral. Okay, and for that case, it will when the spin is full integral, so then it will be called as it will follow the Bose-Einstein statistics, and it will called as boson. Okay. Similarly, if the spin is half integral, then they follow, then their wave function becomes antisymmetric. Okay, antisymmetric wave function. They follow FD stat, and they are called fermion. So this is our total scheme. Now, why this happening? Anybody till now don't know why the full integral scheme are symmetric and why they are following a different statistics. Even when the spin becomes half integral, their statistics are different. So this is still unknown, but this happens. This has been observed. First, it was only considered as fermion, as quantum particle. Then you know that SN Bose basically figured it out that there may be one more probability, and he wrote to Einstein, and then it was called the Bose-Einstein statistic. So that is the full integral spin. Okay. So now, how you can account this thing? So this is very important. One very popular, famous phenomena that will be derived from here, and this class is very important in terms of your competitive exam as well, because in that exam, these questions are frequent. Nowadays, they ask this type of question because it's quite difficult, not difficult, advanced, rather I should say. Okay, so let us consider a two-particle system. How you can differentiate between boson and fermion, that we want to discuss. A two-particle system. It may be H2, it may be HD, something. There are only two particles. So I'm just naming this particle as 1 and 2. These two are particles. Okay. And the wave function will be psi 1, 2. This is the wave function for this particle. This is psi 1, 2. Okay, is it clear? So this particle is termed as 1 and this particle is termed as 2. And this is the overall wave function. Overall wave function for these two particles, this is psi 1, 2. If there is any doubt, you can ask me, okay? Now, this is a permutation operator. Permutation operator means uh, when permutation operator operates on this psi, it changes to psi 2, 1. Okay, why this is? Let's say let me differentiate the color, change the color. This is psi 1, 2. Now, when it is changed, so now this is 2, this is 1. So this wave function becomes psi 2, 1. So is it clear? These two are different. Psi 1, 2 and psi 2, 1. These two are different. There are two particles, 1 and 2, and this ordering is signifying the position of the particle. Means it may be HD or it may be DH, like this. So ordering is also important. What does it mean? It means that in first position there is particle 1, in second position there is particle 2. And this means in first position there is particle 2, and second position there is particle 1. So, okay, so you can think like that. This is this green. Okay, let me write it clearly. So this is, let's say this is particle position 1, this is position 2. This is position 1, position 2. And this green one is particle 1. Green one is particle 1. Let me clear it very. This is particle 1 and this is particle 2. So you can see here the particle 1 is the first position, position 1. So this is not the particle, these are the position. These are position. Okay, so here it should be 1, 2 and it is 1, 2, 1. So is it clear right now?
Yes.
So okay, so when you are applying this permutation operator, what is it does? It just exchanges the particle, moves particle 2 to 1 and 1 to 2, just shifting the particle. Means permutation. So that's why it's called permutation operator. So this is happening. It's just change the coordinates of the particle 1 and 2. Okay, so now we are considering the quantum mechanical particle. So quantum mechanical particles are indistinguishable. You know that if it is
Yes. Yes.
electron, so these are indistinguishable. So essentially, you can't distinguish between 1 and 2, right? Obviously, you can't
Yes.
distinguish. So as you can't distinguish between 1 and 2, then what you can say? What it should be? that
Psi
must
1 2
be,
equals to psi 1 2.
no, there is a catch. You can say that this equals to this.
Yes, probability.
Probability are the same. Okay. So that is possible. So what does it mean? So from there, you can't directly write that psi 1 2 is equal to psi 2 1. That is not the case. When you are saying the overall system should be same, so finding probability must be same. So that is guided by the mod square. So psi 1 to mod square equals to psi 2 1 mod square. So from here, you can write what you can write. Psi 1 2 is essentially will be equals to, there are two options. Two options are probable. Um, First is, let us do it. We consider it. Should I introduce the psi? 1 minute. We, there is a more formal way. Should I do that? Let me think it on.
Plus minus.
No, no, that is correct. Plus minus is correct, but that is not the right statement actually. It should be like this. Okay,
Okay.
is it clear? So it will be power because when you take the mod, so what will happen? E to the power I theta into e to the power minus I theta. So that will gives 1. So that's why I thought that from here you can derive this, right? It is not
Yes.
difficult. When you take mod, it will be there. So what does it mean? It means that you have shifted the wave function by a theta degree. This is called the rotation by theta degree. So when you make 0 degree rotation, so when you make 0 degree rotation in a three-dimensional case, only two rotation is possible. One is 0 degree rotation and another is 180 degree pi rotation. So that's why we obtained it psi 1 2 is equal to plus minus psi 2 1. So we
Yes.
write, when we write a square plus b square, that a equals to plus minus b, it is correct when you are considering in real case. If it is not real, then it's not true. In case of complex case, you should write it b into e to the power I theta. Then it is clear. And theta is the in between angle between a and b. So, but when you are considering only the real, then it's okay. So that is not true. Taking root only plus and minus 1 is not the correct answer. You have to consider the complex numbers as well. Okay, so but here we are safe because we are in three dimension. Why this plus minus is important? That I'm not going to discuss because that will need more knowledge about complex. So that I'm not
Boson
discussing.
and fermion.
No. Boson and fermion that will be defined from this equation. But I'm saying why you can write it. E to the power I theta, when theta is 0, then e to the power I theta will be. So you can write e to the power I theta as cos theta plus I sin theta. You know this.
Yes.
Cos theta plus I sin theta. So when you put 0, so it will be cos 0 1. And when you put pi, theta pi, then it will be minus 1
Minus 1.
e to the power I theta. So that's why for 0, it obtain plus, and when it is pi, it is minus 1. But why these two rotations are allowed only? Other rotation may allow. Why these two rotations are allowed? That I was asking. Okay, so that
Psi
I'm not.
1 2 equals to if minus psi 2 1. That was
Uh,
not for fermion.
no, I'm coming into that. But now understand the math only. The physical
Yes.
significance I will discuss, but the math is clear, right?
Yes.
Okay. So if this is the case, so now we know that what we have defined earlier, that permutation operator P12, when you apply it on psi 1 2, you obtain psi 2 1. Okay. So now you know that psi 2 1 is, you can take this definition as well. You can take this definition. Both definitions are correct. There is no mistake. Okay. Or you can write it in this way again. Okay, let me write it. So let's check it. So is it correct?
Yes.
Just phi is the minus theta, other way of angle. So you can write it. So it will again lead to the same result. Nothing is changed. Okay. So this psi to 1, what you can write now? Just look it carefully. If you uh, two times you can write psi 1 2. So psi 2 1 is essentially two options are there. It is phi 1 2. Okay. Is it correct?
Yes.
So what is the final result? P12, when you apply it on psi 12, it can give plus psi 12. This is a probability, or it can give minus psi 12. Is it okay?
Yes.
Okay. Or forget it. Do it general. Nothing will I will do. Make it. We should make it general. Why I am saying that? Let's consider this. These things you can understand, I guess. Okay. So psi 21. So psi 21 you can write e to the power I 5 psi 12. Okay. I'm not introducing plus or minus, nothing. I will derive that. Why it will be plus or minus. That should be clear. First I thought, okay. So now, if you operate this permutation operator twice to psi 1 to what will you get?
Psi 1 2.
Again, so so essentially this is equivalent to identity operator, right?
Yes.
The this operator has a name. I forgot, but this type of operator has a name. Okay, so this you can write. So now consider this part. This part is essentially psi 21. So it should be. Nothing is wrong. Okay. So psi 21 is equal to, if you apply to psi 12 will be there. Correct. So you can write it psi 21 equals to e to the power I theta into psi 21. Okay. You can write it. Just follow. There nothing is there. Just you have to pay attention. Now you can write it as e to the power I theta is as it is, and e to the power psi combination of psi 1 2. Okay. So it is what we have already written. This I want to again you can write it as e to the power I theta 1 to 2. So e to the power 2 I theta psi 1 to. Check it. Is it correct or not?
Yes.
Okay. Or you can ignore this step. Direct you can write. This is trivial. Okay. Just what I have done. Just I am repeating. Nothing. Here it is psi 1 2 1. So I have put psi 2 1 is equal to again e to the power I theta Sine 1, 2. So that I have just put. So you can write it as psi 1, 2 is equal to e to the power 2 I theta psi 1, 2. It should be. So from here also it is clear. If this is the case, psi 1, 2 is equal to e to the power I theta into psi 2, 1. When you again operate it two times, then obviously 2 I theta will be there. I have just operated two times. What I have done, I am just summarizing. It is psi 1, 2. When you apply the permutation operator on it will be psi 2, 1. When you operate again permutation operator, it will be again psi 1, 2, right? So two times permutation operator we are operating. So when permutation operator is operating on psi 1, 2, it is eventually psi 2, 1. But we know that you can write it as e to the power I theta psi 1, 2 after just
Yes.
one time of rotation. Again you are giving rotation applied to permutation here two times this permutation. Second permutation you are applying. So second permutation when you are applying, so it will be again e to the power psi 1, 2 is there. So you are, this is constant, right? You are applying permutation on this psi 1, 2, so it will be psi 2, 1. So this you can write as 2 I theta psi 1, 2. That's I have just written. You can understand. One rotation you give, you e to the power I theta will come here. So this state is essentially equals to this one e to the power I theta into psi 1, 2, and it will be to the power 2 I theta into psi 1, 2. Okay. So
Parity operator.
yes. Hello.
Parity operator.
Parity operator. Parity operator. Yes. Plus minus one. So it's, you can say parity operator or idempotent operator. You can also say yes. Theta square.
Idempotent.
Yes, but that for idempotent operator, there must be one more condition. Okay, parity operator is correct. Idempotent, I thought that there must be one more condition is there. But is it is clear now? Why it is 2
Yes.
I theta? Okay. So ultimately you can write psi 1, 2 equals to e to the power 2 I theta into psi 1, 2. So what does it mean that e to the power 2 I theta should be 1? Correct?
Yes.
So e to the power I theta will be plus minus 1.
Yes.
That's why I said that it should be plus. That essentially it means that theta is 0 or pi, not degree in radian. From here it is coming. So here it was correct. It is I theta, but you have to remind that you keep in mind that after giving two time of rotation, it should be the same thing. So that's why when it will be e to the power 2 I theta, it should be 1. Okay, so that essentially means that it either plus 1 or it may be minus 1. So from here, two possibilities are coming. Hence, you can write it psi 1, 2 is equal to plus minus psi 2. Okay, is it clear?
Yes.
Oh, so that is the case. Now, when the two cases are there, we obtain first case. Psi 1, 2 is equal to psi 2, 1. So it is symmetric, right?
Yes. Boson.
Mhm. Yes, that I will come later, but it is symmetric. When it is minus,
Antisymmetric.
it should be antisymmetric, correct? These things we have discussed, but did not discuss mathematically. Mathematical part was remaining, so this is the mathematical treatment, antisymmetric. So now this plus sign, the symmetric wave functions. These symmetric wave functions are basically um, that means the particles are identical, and that essentially means that they would have a integral spin. What spin? Zero, 1 in terms of H cross, obviously, 2 H cross. H cross we don't write, so 1, 2 you can understand. But obviously there is a H cross like this. And these are called, why you don't know, bosons, why they followed. And these are called Fermi. And the spin are antisymmetric, means okay, H cross you can write it. H cross. Example, this we have already discussed: photons, phonons, these are boson, and electron, protons, these are fermions. Okay. Now we let us go to a two-body problem that we were discussing in that case. Now we can write it. Now let's say psi. Let psi 1, 2. Explicitly, if you write, so you have to write it as, just understand it, psi A1, psi B2. That means I am just giving the name of this particle. This is just A for avoid confusion, and it is B. So just copy it. Condition we obtained. Now we can do it explicitly. So this particle is green one. Green particle is A. Green particle is A, and this blue particle is B. Here green particle is A, blue particle is B. So you see psi 1, 2 is essentially psi. Now we can write in terms of individual particles. This was the total wave function, right? Composite wave function. You know that wave function are multiplicative. So eventually it will be the multiplication of two wave function. This is the wave function for the first particle psi A, and this is the wave function for second particle psi B, and these are the coordinates 1 and 2. So is it clear how the I have written this, the formula to write the composite wave function? Okay. So what will be this psi 2 1? If you want to write this, so it is, what is this? This is psi B,
Psi
psi
B1.
psi B1, psi A2. Or you can write it psi A2, psi B1, whatever you want to. So this is the wave function. You know that when you operate permutation here, so you will eventually have this. No, no, no. This, you know, 1 plus minus 1, 2. This you know. Or if you apply the permutation, then it will be converted to psi 2 1. The reference elements that we have discussed this. Okay. So now one thing you have to check, that it should be what we have discussed, that it should be the symmetric psi 1. So let us consider the boson. For boson, psi 1 2 should be equals to psi 2 1. The symmetric, this we obtain na here. You check.
Yes.
So that I have written here. What does it mean? That psi A1, psi B2 equals to psi A2, psi B1. So this should be the case. This should be equal. But this is correct. There is no. But in case of fermions, should be equals to 2 1. Okay. Okay. This should be followed. But you can, now you can check it whether it is correct or not. Is this really antisymmetric? what I'm saying. Psi A and psi B, these are A and B, these are indistinguishable particle, right?
Yes.
Indistinguishable particle. So what you can write? You can write psi A equals to psi B. Wave function should not be changed. If it is a hydrogen
Yes.
atom, though, psi A and psi B should be the same. Position, coordinate I forgot, but this should be the same, right? So here, if you put it, you will obtain that psi. This is correct. Just incorporating that. So it is matching. Okay. But here,
Yes.
if you put it, what we will have? Psi A, psi B2, psi A1. So is it matching?
No.
Minus sign is appearing. So that means, what does it mean? It has a great claim that this psi 1 is not a acceptable wave function for fermion, neither psi 1. This is not the acceptable wave function because these are not antisymmetric. And if it is antisymmetric, then they must follow this minus equation. It should equals to a minus sign. But this part equals to this part if you ignore the minus sign. It is not following that relation. For boson, it is okay, but for fermion, it's not okay. But you know that the wave function should be the general wave function. So that's why you
Can
have
you please
to,
repeat?
okay, this part you understand that
Yes,
if
fermion.
if psi 1 2 is a valid acceptable wave function, that then psi 1 2 should equals to minus of psi 2 1
Yes.
for fermions. But if psi 1 2 is equals to psi A1 psi B2, then what you can write? Psi A1 is psi B1 and this is psi A2 because you know these things.
Yes.
So what does it mean? Psi 2 1.
Yes.
So psi 1 2 and psi 2 1 are same with a plus sign. So this establishes the boson relation, not the fermion one.
Yes.
Okay, so that essentially means that this is not a valid wave function for fermion. It can represent a boson, but this is not an acceptable wave function for fermion because it's symmetric. It's not antisymmetric.
So what's the correct form?
That I will discuss what should be the correct form. So obviously that we have these two particles. So we can't have any other particles. So we have to have the correct wave function from these two particles. Other means this psi 1 2 is not correct. So let me drop it here. Yes. So this psi 1 2 you can't write psi 1 2 as what we have just proposed. This is not an acceptable form, right? This is not an acceptable form. So what form you can propose? Just think what can be the right form. In quantum mechanics, what you have done? Think it. If you remember the p orbital, then while solving the hydrogen atom, you obtain three quantum number, right? 0, +1, and -1. 0 was
Yes.
pz. +1 and -1 was,
Px, Py.
which one is px, which one is py?
Plus is x.
And it is py. Why? So this is not the correct answer. Let me write. This is 0. Let's say it is plus, it is minus. If these are the wave function, then psi 0 is equivalent to pz. But this is the px and this is the py. Okay. So
Yes.
so we have to take the linear combination
Yes.
because these can't fulfill that antisymmetric condition there also because that's the
Yes.
electron that should follow the antisymmetric condition. Here also the same case. That's a fermion. So antisymmetric condition should be followed. So for that we have to take the linear combination. So what form we can write? That psi 1 2 equals to just the acceptable form I'm writing psi A1 psi B2 minus psi A2 psi b1. The linear combination of that form. Linear combination means not only the plus, also the minus, and obviously here will be 1 by root 2 to normalize the wave
Yes.
function. So this is accepted. How? Now we can check it. This is psi 1 2. Okay. So what will be psi 2 1 now? Psi 2 1.
1 over root 2
Just we have to exchange the coordinate.
2 psi b1.
Correct?
Yes.
So essentially it is minus of psi 1 2. It is straightforward, right?
Yes.
So, so it is now antisymmetric. So this is the correct wave function for fermions. And for boson,
It is plus.
it is plus. For boson, this is also allowed. So you don't think that this is not allowed. This is allowed for boson as well. This is allowed and also the plus combination allowed. Other combination you can try also. For n particles, you can think way more way more these permutation combinations are allowed. Here we are considering only two particles, so that's why you have this limited option. Okay. So this is also both wave functions are allowed for bosons. So now for fermions, antisymmetric wave function psi. This is 1 by root 2 psi a1. These are the particles and these are the position coordinates. Okay. So what you can write? What you can write? Let's see. You can write it.
Yes.
What is this?
Determinant.
Yes. And this is called, do you know what does it call? Flatter determinant. So for fermions, you can write the wave function for fermions through this flatter determinant. Why it is easier? So it is two particle, but for n particle, it is writing in this form is very difficult. So in this way, you can easily write it. So just see how the things goes on. For n particle, how you can write? Let's say for n particle antisymmetric wave function 1, 2, 3, there are n particle. So the scatter determinant you can write. Just see through this row, this just particle is fixed. This is a particle and the
Yes.
coordinates are changing. So it is essentially
Psi a1, psi
a1,
a2, dot
phi
dot psi an.
a2, phi a2. This will be phi b1, phi b2, which goes up to phi bn. And through this column, the particles are changing. So it is psi n1, psi n2, psi nn. So through this data determinant, you can easily write it. And obviously, there would be a factor, that is normalization factor 1 by n factorial. So this is our scatter determinant for the antisymmetric wave function, which essentially represent the fermions. Correct?
Yes.
Okay. Now boson. For boson, how you can write it? 1 by 2 1 by 2 was there. Psi a1, psi a2, psi b1, psi b2. It's called consonant. Okay. When the in case of determinant, it's minus. If it is plus, so it's called consonant, I think. Yes. Okay. So everything will be same.
Consonant.
Yes, I just let me check the term. I think it's consonant. I have written down. It is mathematical term, but essentially it does not require. Okay, let me again. 1 minute.
Same as determinant plus in the middle.
No, not same as determinant. In case of determinant, it is negative.
Yes, it is positive. Only
It
that
is,
difference.
yes, but the term, let me check it. Yes, here I will. This is like a determinant, yes. Where it is difficult to find out. While taking these notes, I write those things. Oh, no, sorry. This is the term. Permanent, okay? Permanent. This is the correct term. I'm writing there. So it is called the permanent. Okay. For n, then it is clear. For n particle, it will be just the sum. Is it clear?
Yes.
Okay. So this is for boson and this is for fermions. Okay. But now there will be a great thing. So for two particle case, what we have obtained, the function is psi a1. I'm just ignoring that normalization factor. This is our function. So there are two now if you think, let's think that both particles are in the same position. First, we have considered that particle A, this is particle A at position 1 and particle B at position 2. This is one case, and we have taken the linear combination of other case, this. But let's say if both particles are in the same position, A and B, then what will be the wave function? What will be the
Psi one.
psi A1, psi B1, right?
Yes.
Minus psi A1, psi B1,
0.
so 0. That's why two fermions can't be resided in a same energy state or same state.
O.
This is the Pauli exclusion principle. Pauli's exclusion principle. Here also from here you can think uh, this determinant thing. So this is a determinant. So when you make, if you make the two particles in the same position, then this will be all the same. This position will be the same. So if the position are same, let's say all are 1, 1, 1, 1, then two columns are equal. And you know, for a determinant, if two columns are equal, then it will be
0.
0. Here also it is clear. So that is the reason why fermions follows the Pauli's exclusion principle. So Pauli's exclusion principle is not a new thing. It's an artifact of that thing that fermions follow the antisymmetric function. So that is the reason. To make the wave function antisymmetric, the Pauli's exclusion principle should be held. Now,
That
why?
concept is coming from here.
Obviously, total concept, the exclusion principle used studied in class 11, that in one energy level, two part there you have considered it was written in different language. Four quantum numbers can't be same like this.
Yes.
Means that means the same. When the quantum numbers are same, means that are same energy level. So here two electrons can be there, you think, but here two electrons can be there means these are not the same energy level. When you are considering the spin, it is again split in two parts, plus half or minus half. So then it is plus half is there, minus half is there. So in a particular energy level, one energy level, only one electron can be there. Okay, either
Okay.
up spin or down spin. Yes. So here, in terms of this approach, we write this, but these are the different thing. One is plus or minus up. So this actually gives also the idea about spin. So you see here, spin is very important. That essentially distinguishes that energy levels. Okay. So in case of boson, there is no restriction. That is symmetric. So there is no restriction. Infinite number of particles can be reside in a state. And Maxwell Boltzmann, you know, there is no symmetry, anti-symmetry. These things are not there. These things, actually, this symmetry, just understand this thing, symmetry, anti-symmetry, this part appears due to the spin. Because first we have already stated that here, when the spin is full integral, then it follows the symmetric wave function. So this nature that for boson, the wave function should be symmetric, that is due to their spin. Because that particles have the full integral spin, they have to have the function symmetry. And they have the, if they have the half integral spin, the wave function should be antisymmetric. So this symmetric, antisymmetric, these are totally due to the spin. If the particle does not have any spin, there is no symmetric, antisymmetric, these things. So that's why in case of Maxwell-Boltzmann particle, that's a classical particles. And you know, in classical particles, there is no analog of spin. There is no analog. So you can think like that this is a, whether this camera is on or not, I don't know. Okay, it's on. So, so if you consider this is a particle, classical particle, and you think this is a spin, this is not. Just understand there are two types of angular motion. One is orbital motion, like this revolving, and one is this. This you consider as spin, but this is not actually a spin. This is actually rotation. Means this is, you can think like that. This is actually rotation around its own axis. Do you
Yes.
understand? So this is not the spin. So we essentially actually confuse with these two things. Orbital motion is totally different. That's clear. Okay. In physics, in case of angular motion, do you have ever studied spin angular motion? Always you have
Spin
studied
angular momentum.
orbital angular momentum you have studied. You remember in case of
Yes.
11, 12, there was anything about spin angular momentum or spin motion, anything was there?
No.
Because that is not possible in case of classical thing. So this is not a orbital angular motion. So it is not a, it is just revolving around its own axis. So this is the same, this is orbital motion is different thing. That is angular motion, but that is not angular motion because the nothing is changing here. It's not creating any states. So essentially, you have to understand that that is not a that is, we also call that is also in terms of language it's spin, but in scientific term, the spin is totally a quantum mechanical phenomena. Spin has no classical analog. Orbital motion has classical analog. Mass has classical. These things are classical analog, but some features are there in quantum mechanics which does not have any classical analog. So that we can't imagine even when I said that electron is revolving around nucleus, that is the orbital motion, that you can think that like our earth is revolving like sun. But when it comes spin, the spin of electron, you can't think because you don't know. In classical mechanics there is nothing like that, like tunneling. In classical mechanics tunneling is not possible. There is nothing
Yes.
like tunneling. So you can think what is tunneling, you can't think. Uncertainty. In classical mechanics there is no uncertainty. So you can think about uncertainty, you can visualize in your brain what is uncertainty. So that is not possible. These things are there in coherence. Coherence is also there. In classical mechanics, coherence is not possible. So these are called pure quantum mechanical phenomena. This is totally due to the quantum mechanics. So here also this is totally due to the spin. So when you are considering the Maxwell-Boltzmann particle as they are totally classical particles, so there is no question to have spin. So that's why these three statistics are different. They should be different. Now there is a $1 million, $1 billion question that why that till now is unknown. Why the full integral spin are symmetric? Why they have to follow that criteria to be a boson? Another one find out. Just you see two categories of particle. This is truly amazing. One is, let's say one has a full integral spin plus 1, 2, 3. These particles will follow different properties, different laws, different physical phenomena. Everything will be different. Later you will see everything, distribution function, everything is different. Total behavior of that another particle, just they have a different kind of spin, plus up, minus up, plus 3/2, plus 5/2. These things, they will be totally different. Their total criteria, characteristics, everything will be different. So this is truly amazing. So one thing you see here, the exclusion principle. Due to this exclusion principle, these two particles become very much different. In case of boson, in any energy level, there will be infinite number of particles. But in case of fermion, there is a huge restriction that in one level there will be only one particle. So, this is okay. So बहुत ज्ञान हो गया चलो. Next. Now these things in this class also discussed. So I will not discuss this. I will just state these things and then I will discuss the part which was not discussed in class, but the result was discussed. So that we will discuss that. Counting of microstate under this distribution. Actual counting of microstate in Maxwell-Boltzmann Fermi-Dirac Bose-Einstein. Okay. So for Fermi-Dirac, sorry, let me start with the Maxwell-Boltzmann. Okay. One thing you have to remind, just for Q equal to Q to the power n. Do you remember this?
Yes,
Okay. And this. So what was the
by n
difference?
factorial.
Yes.
Distinguishability.
Yes, it is distinguishable, right? And it is indistinguishable. But what kind of particles are these?
Quantum particle.
No, both are classical particles. Both follow the Maxwell-Boltzmann statistics.
Indistinguishable.
Even so, we are considering generally Maxwell-Boltzmann particles are distinguishable. But if they are indistinguishable, then it will be q to the power n by n factorial. Never we have considered the quantum mechanical behavior. Bosonic or fermionic behavior we never incorporate. Bosons somehow follow this, you can think, but fermions never. That I have already said. So these are the indistinguishable Maxwell-Boltzmann particles. So remember, we are considering the gas molecules that are indistinguishable, but never we discuss about electron or phonon like this because they are not Maxwell-Boltzmann particles. They are quantum mechanical particles. Gas molecules are Maxwell classical particles because in case of gas molecule, we have studied the kinetic theory of gas. That is totally classical thing. Nothing is quantum mechanical there. So these two are different, but here we will see the quantum features that we will incorporate here. So before that, the microstate, number of microstate under Maxwell-Boltzmann statistics. This that we have already discussed. If you remember, n factorial, then I is equal to just I, let me write I, gi to the power ni divided by ni factorial. Do you remember this?
Yes.
Hmm. So this is the when there are ni is the number of particles in the energy state ei, and Gi is the degeneracy of that energy state. Correct? So this is the case, and when there is no degeneracy, that formula we have used widely. This was that formula when there is no degeneracy. So this is for Maxwell-Boltzmann, right?
Yes.
So now for Bose-Einstein, we did not prove it. We just write down that. That is the formula Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. So here also I will not prove it. Because to prove it, it is not a mathematical proof. You have to understand it. So I will upload the total note of this part. From there you can see that is written, handwritten notes, my MSc notes. So from there you can see it, but it is you have to understand it. That's why I'm not doing this, but you have to understand that this is a symmetry. Symmetry it must be symmetric because it's for boson. So while proving this, we have to consider the symmetry nature. And for fermion, that will follow the Fermi-Dirac statistics, and for there the formula is yes Gi factorial divided by n I n fact no, ni factorial Gi minus n factorial. So these are the three formulas: Maxwell-Boltzmann, Fermi-Dirac, and the Bose-Einstein.
In Thermodynamics, there should not be any degeneracy.
Why?
No two particles can exist in same energy
So
level.
degeneracy means number of state with the same energy.
Okay.
Particles may not be there. You can say that Gi must be greater than Ni
Yes.
for Fermi-Dirac, not greater equals to Mn. That should be because number of particles must be uh, equals to the degeneracy because part one state there will be only one particle at max. It may be 0 or 1. Na? 1 is the maximum. That may be vacant. Vacant is allowed. So Gi is must be greater than or equals to Ni for Fermi-Dirac. So now you can guess what is the maximum and what is the minimum among these three. So one thing you see here, for these quantum particles, if there is no degeneracy, then it will be, just see, if degeneracy is not there, then what will be the result? If let's say Gi is equal to 1 for next
One.
state. So let's put it here. So it will be 1 minus 1, so it is 0, so it will be 1. Correct?
Yes.
It is also 1, right?
Yes.
If there is no Gi is 1, so it is straightforward 1, correct? And if you put it here, so it will be 1 by Ni factorial into 0 factorial, uh, not 0 factorial, uh, Gi minus
One
Ni fact.
minus one.
Now Gi is 1, so Ni would be either 0 or 1 because you have
Yes.
to follow this condition. So when it is 0, then also it is 1. If it is 1, then also it is 1. So always will be 1. So for
When it is
quantum,
one, then the
if Gi is 1, then
and Ni is
Ni
also
may.
one.
So these two possibilities are there, correct?
Yes. Overall factorial.
No, no. If for a particular state, if level, if Gi is 1, degeneracy is 1, then Ni must be 0 or 1 because you have to follow this condition.
Yes.
That means there is only one state, one particle can be there or no particle can be there. So when it is 0, then what will be the answer? 1 factorial by
One.
0 factorial, 1 minus 0 factorial. So it is 1. So when it is 1, so then it will be 1 factorial by 1 factorial into 0 factorial. So again it is 1.
One.
So for both cases, there will be. So for quantum mechanical particles, so degeneracy must be there. If there is no degeneracy, then only one microstate will be possible. So it is very, very important. So everything is due to the degeneracy for quantum mechanical particles. So you see, the classical particles obviously much more accessible state will be there, more degeneracy will be there because here only if you have degeneracy, then only you will have the number of microstate. Or you can understand why the degeneracy is needed. Just think, if there is infinite number of levels, and you have any particles like two particles are there, let's say. So this is under one orientation. Obviously, you have to keep in mind this. These are the microstate under a particular orientation or configuration. So let's say there are, I'm just saying, three states are there, and you have two particles, and this occupation number orientation is, let's say, 1, 1, and 0. So only you have this one option. No options is there because these are indistinguishable particles, quantum mechanical particles. If it is A, B, then you can have B, A, B, these things. But here you can't. So only one possibility will be the one. So that's why if there is no degeneracy, but here you can see if there is, let's say, degeneracy is there, then you can have other option. This is option, this is option. So two options are there. So only for quantum mechanical particle, if there is degeneracy, then only more than one possibility will be there. Okay. So obviously it is clear that Maxwell-Boltzmann will be maximum, then Bose-Einstein and Fermi-Dirac will be least because there is another one constant is there that Gi must be equals to greater equals to n. So is this clear? So you can take any example. By taking any example, you can check. Okay.
Okay.
Now what I want to discuss that is important that this part also discussed in class, but the result now this equation was not discussed in class, so I thought to do it. Okay. For first we will do for Maxwell Boltzmann. So for Maxwell Boltzmann, this is n factorial this. So we have to evaluate what we have to evaluate the most probable distribution. Okay. Under what does it mean? Let's say 1, 1, 2. This is the occupancy. Suppose four states are there: A, B, A, 2, 2, 1, 2, 1. Let's say. So it is A, B, C, D. So this is a distribution A, C, D, B. This is a distribution. These things are there, right? So this is one distribution, one configuration. Under this configuration, this is the number of microstate. So we have to find out the most probable configuration. Other configuration maybe there 1, 2, 1 is there. So here you can find out what will be the total 2 factorial, 1 factorial, 1 factorial. What is the answer? 12, right?
Yes.
We have 4 particle and 3 state. So this is another one. This is another one. So it will be 4. Just like canonical ensemble thing. There was also more than one configurations, and we had find out the most probable configuration, which was all are the equally filled. If you remember,
Yes.
in last class we did, and we only considered that distribution, the most probable distribution, by indicating a star, that Dirac delta function like things. Here also
Yes.
we'll do the same thing. Here also we have to find out that most probable distribution because we know that most probable distribution is way more probable than other distribution. So we can ignore other distribution. We will only consider the most probable distribution. That is our motto. How we did that? If you remember, we differentiate that ln gamma and make that 0, and from there we derive the condition. From there we derive the partition function. Correct?
Yes.
Here also we did the same. So here also we will consider ln gamma. So it will be now ln n factorial plus summation ln ni ln, right, minus I ln ni factorial. So is it clear? I think it's okay. Okay. So n, now we will apply the starting approximation. If there is any mistake, you can say me, because it is ni ln ni. Okay. Ni ln gi minus ni ln ni. So we can take ni common and gi by ni. You can also do that. So let me. So up to this is clear.
Yes.
Okay. So we have to take the derivative. If you remember, we take derivative, not this we did not make zero. We introduce the Lagrangian undetermined multiplier. We have to
Yes.
consider the restriction. What are the restriction? The first restriction is overall number of particles is constant. That's why we cut it. And another one is
Energy
the
is
energy.
constant.
Exactly. The same thing. In that case, we deal with the canonical ensemble state. Here, this is the molecular state. The same thing.
Yes.
So these two constants are there. So we have to consider these constants. So you can write it as like it. You can write it sum over. This means del n is 0. Correct?
Yes.
So you can write it delta sum over I ni is 0. So here also you can write delta sum over ni epsilon I is 0. So these two are constants. So you have to have delta ln gamma Maxwell Boltzmann minus a constant. This is Lagrangian undetermined multiplier ini minus beta delta epsilon I ni. So this you have to make 0. Is it clear? The same treatment we have done.
Yes.
Nothing new, just the this is molecular case. So put it. This we have obtained. So I will put it. So it will be. So it is not del. So this is normal. So del we have to. So delta n ln n minus, not minus, plus over I ni ln gi minus ln ni. Then minus alpha delta over I ni minus beta delta epsilon I ni is equals to 0. Okay. So this first part is 0 because n is constant. Second part, this is the second part. Okay. So how you can write it? We can take out the sum, total sum, then ln gi minus ln ni minus alpha minus beta epsilon I, then ni, not ni, dni. Just check it. Other things are there, only dni is there. Is it correct?
Yes.
No, it's not correct. Just check it again.
Okay.
GI is okay. This means
Yes.
ln GI into del ni. Okay.
Beta epsilon I.
Beta epsilon is there. But here you see ni ln I. Here two ni is there.
Yes.
So when dni is there, so lni is there. But one more term will be there. D of lni. So that will be 1 by ni. So ni into 1 by ni. And that is minus 1. Is it understandable or I should write it? Just see delta ni ln ni. Just look at this. So you can write it delta ni into lni. This is one term plus ni delta of ln ni. So it
Okay,
is,
clear.
so just let me also complete it. ln ni plus it is just 1.
1.
So that you 1 into dni obviously. So that you have to consider. So that's why this minus 1 is there. Minus is because there is a minus sign. So then it should be 0. And you know, this can't be 0. So only this part should be 0. So you can write ln gi minus ln ni minus 1 minus alpha minus beta epsilon I is equal to 0. Here we will put a star. Why? This is now become a most probable distribution because we are considering
Yes.
the 0. So ln gi minus ln ni is become alpha plus or alpha prime plus beta epsilon I. Same thing we did alpha plus 1, we change it to alpha prime. Here also I'm doing the same thing. So from here you can write, so ni or gi by ni is equal to the power alpha prime plus beta epsilon I. So ni will be gi into to the power minus alpha plus beta epsilon I. So this is an alpha. So most probable distribution ni star will be gi divided by e to the power alpha plus beta epsilon I. So is it clear?
Yes.
Why I have written alpha instead of alpha prime? I have written alpha. Why?
Arbitrary constant.
Dummy variable. Whether
Yes.
this is
Prime variable.
alpha prime or alpha anything is same. So this is for the Maxwell-Boltzmann distribution. This is now this is not called partition function. This is not partition function. Okay. Because
Okay.
in case of partition function, you remember there was the denominator. This part there was sum. So that due to that summation, it was the same thing. Thing is same because when you take the summation, there will be summation again here, and that will be called the partition function because we are considering pi that was ni by total n. So that's why you have to take it will be gi divided by e to the power something. This is ni, and for capital N, the sum will be there. So eventually it will become e to the power alpha plus beta epsilon j divided by sum over these things. This was obtained, right, and this was called the partition function. So here we will not uh, here we will not derive that part. From here we can do that, but that is not important here. Here this ni factor ni star is important. This is not probability. This is the number of particle. Pi is the probability of having the particle. This is the number of particle at that ith energy state. So this is called probability distribution. Sorry, the number distribution, or in general called Maxwell-Boltzmann distribution. Okay, so this is the case. So this is true. Now we'll have to check for our second target, that is Bose-Einstein. The same treatment I will do. Nothing is there. Just instead of this form, we will have to consider the Bose-Einstein. It was this. So what you have to take first? Logarithm. So eventually it will convert it to summation ln ni plus gi minus 1 obviously factorial minus sum over I ln ni factorial minus sum over I ln gi minus 1 factorial. So now we'll apply the Stirling approximation. So everything has a sum, so we can take that sum common. So it is n ln n. So we can write it. Okay, minus n. Oh, sorry, n ln n minus n. Okay, I think it's there. Just I have used the Stirling approximation, nothing new I have done. Okay, so what will be cancelled? This, if you open this, then it will be minus minus plus. So eventually ni will cancel. So again, if you open this, so it will be this gi cancel, 1 will be cancelled. Okay, so only we have sum over I ni plus gi minus 1 ln ni plus vi minus 1 minus ni ln ni minus gi minus 1 ln gi minus 1. So is it clear?
Yes.
Okay. So here one approximation they have take, usually we take. So that is that if you take that approximation, then the calculation will be easier. So that let me consider this obviously approximation. We can ignore that one because ni and gi, this is the
Are
number of
huge.
huge. And how huge we can think that I'll say that in next class that it is huge means ni and gi are in the 10 to the power order. So eventually you can think if it is even 10 to the power 3, then also it is ignorable. So then you can directly write it like this. Just I have ignored that one compared to this other parts. Okay, so what will now we have to take the delta. Okay, so for first term it will be, so here two terms are there eventually ni, so delta, if you know, so it will be delta ni plus gi, then ln ni gi. Okay, one part is this and another part is ni gi, ni plus gi, delta ln ni plus gi, the same. And next it is delta ni ln ni minus ln delta ln ni. Same again, it is g. So delta g will not be there, so you can ignore that g. So just these two part will be there. G will not be considered. Okay. GI is delta GI. How we can degeneracy will not be changed. Obviously, particle can be transferred. GI how can? So this is okay. So I think now if you open it, so it will be delta Ni ln Ni plus Gi plus delta Gi, and delta Gi you know that is 0, so that will not be there. Next part is Ni plus Gi. This will be 1 by Ni Gi into delta Ni, and again these things you know, this will be delta Ni ln Ni, and it is minus dn. So you cancel out. And dni will also be cancelled out. So it will be eventually sum over I ln Ni plus Gi by Ni. I think yes, nothing is there into dni. Just check it whether it's correct or not. Is there anything? This will remain only. This dni and this dni will be cancelled out.
Yes.
So this only this term appears. So if you don't ignore this one, then it will be the same result will come, because when you differentiate with respect to one, eventually that will be 0. So result will be similar. One will be there as well here, but oh, that is correct. So now we have to write in terms of Lagrangian undetermined multiplier, like this is, you know, same thing, nothing new. This should be 0. Delta will be there. So first part is we have derived. This is sum over I dni. If you take common, then from first part it is ln Ni plus Gi by Ni. From second part it is minus alpha. From third part it is minus beta epsilon I. So it is 0. So this term should be 0. So from here you can write, now it will be star, because it is now most probable distribution, equals to alpha plus beta epsilon I. So you can write 1 plus Gi by Ni star equals to e to the power alpha plus beta epsilon I.
Yes.
So Ni star will be 1 by e to the power alpha plus beta epsilon I minus 1.
-1.
So this is the most probable distribution. No, Gi is there.
Yes.
So this is our now distribution function for the bosons. So see what is the difference? Only this minus 1 terms added. Rest of the part is same. Just minus 1 is added in case of Bose-Einstein distribution. Fermi-Dirac, you will do yours by your own. It will be
Okay.
same. It will be same. The result I am writing for Fermi-Dirac, not just you have to follow the same procedure, and you will obtain for Fermi-Dirac Gi divided by e to the power alpha plus beta epsilon I plus 1. This is for Bose-Einstein Fermi-Dirac. So in general, if you want to write, so it will be n I star equals to Gi divided by e to the power alpha plus beta epsilon I plus eta. Okay.
What is this?
I'm writing. This is the in general expression. Just make it okay. Where eta is 0 for Maxwell-Boltzmann, eta is +1 for
Both
Bose-Einstein,
Einstein.
and eta is
-1 for
-1 for
Fermi-Dirac.
Fermi-Dirac. So this is consistent for any equation you will see in Bose-Einstein. Just replace plus with the minus. It will be Fermi-Dirac. And you ignore that, it will be Maxwell-Boltzmann.
Always, every equation.
Every equation. Because every things you will derive from here, that will be according to this distribution function. So in general, every equation is written in terms of this plus minus, plus minus, plus minus. That will be carried out. So this is the general expression. Okay. So why I did this now? One thing is important. Now we have to consider one special case that is important. Fermi Dirac you have to do. I skip to do this special case. Take a special case where GI is very greater than Ni. Why I am taking this special case? GI is very greater than Ni. That means for a particular energy level, there are way more number of degeneracy compared to the number of particles. Okay. Next class,
Okay.
these things I did not show you, but next class I will show this ratio gi to the power ni is 10 to the power 11 times. So you can think for a particle, there are a huge number of level accessible. For a gi is a degeneracy, so we are stuck in a particular level, ith level. Here, there are degeneracy, right? So there are degenerate level. These are degenerate levels. So if you calculate the number of degenerate level, that is gi, and the number of particles, that is ni. If you take the ratio gi by ni, it is huge. If you, I will do it in the next class. So it will huge 10 to the power order 10, 11. So essentially you can consider gi is very greater than ni. So if gi is very greater than ni, then this formula how the formula will be changed, that we can do. Okay. So this is called classical limit. In case of classical limit, this essentially happens when the temperature is high and density is low. Density is low means number of particle is low, and temperature is high means gi is higher. So that condition. So what do you expect under this classical limit? Just guess it.
Many number of state accessible, more number.
That's okay. But what will be the ultimate thing? If you impose this condition under the distribution you obtain, what changes you expect? It is classical limit, right? So
Yes.
quantum features will not be there.
Okay.
So Maxwell-Boltzmann and Bose-Einstein statistics should be reduced to Maxwell-Boltzmann statistics.
Yes.
So that you can prove it. So let me do it. Okay. So take the Fermi-Dirac. So Fermi-Dirac, in case of Fermi-Dirac, this is always true. So that is not the case. Here, this is the classical limit. It is very greater than. So for Fermi-Dirac, it was gi factorial, ni factorial, gi minus ni factorial. Okay. So you can write it just this part. This gi factorial divided by ni factorial into gi minus ni factorial. So you can write it like gi, gi minus 1, gi minus 2, and so on. Gi minus ni minus 1. So this is, instead of bracket, I can give this gi minus ni, gi minus ni plus 1 and up to 3, 2, 1. So this is our factorial. So, and it is ni factorial. And if you open it again, so it will be gi minus ni into gi minus ni minus 1 not minus 1 it is plus 1 gi minus ni plus 2 and goes up to 3 to 1. So you see this part will be totally cancelled out and only remains gi minus 1 to gi minus ni minus 1, and here is ni factorial. Okay, so from here what you can write, this you can write, just check it,
Yes.
because here each term is less than gi. So this is gi, this is less than gi, and every term become less than gi, so it
Yes.
essentially obviously less than this. So you can write gamma Fermi Dirac is less than gi to the power ni by ni factorial. Okay, correct. You can write it, not gamma Fermi Dirac, sorry, this part. So in case of gamma, then it will be this. Some you have to take this I. So is it correct? Check it, check it.
Yes.
This part is less than this. When you put this pi, then obviously this, if you put this pi, it will be gamma fd, omega fd, and this is just this. So what you can write this? This essentially means this is less than the Maxwell Boltzmann by n factorial.
Yes.
Okay, so that you can write.
Okay.
Now take the Bose-Einstein. So Bose-Einstein was ni plus gi minus 1 factorial divided by ni factorial ni minus, what I'm right? Yes, yes, yes. This is our Bose-Einstein. Yes. So let consider hi variable shift gi minus 1. So what you can write? Factorial divided by factorial hi factorial. Okay. Now this ni plus hi factorial divided by ni factorial hi factorial. Again, you can break it down. So it will be ni plus hi, ni plus hi minus 1 up to, we write it ni plus hi minus 2 up to 3 to 1. The denominator will be, this is ni factorial anyway, and this is hi, means hi minus 1, hi minus 2, and so on, 3 to 1. Okay, is this clear? I
Okay.
think. Okay, so what you can write? So you can write it the seat NiHi into Ni plus Hi minus 1 into Ni plus Hi minus 2 dot 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 Ni plus Hi, Ni minus 2, Ni plus Hi, Ni minus 1, Ni plus Hi minus Ni, then Ni plus Hi, Ni plus 1, and 3 to 1. So is this understandable?
Yes.
Okay. So when you are coming from Ni to Hi, Ni plus Hi, let's say, just take an example. Ni is 5, Hi is 4. Just I'm saying. So you are writing 9 factorial, that means 5 plus 4 factorial divided by 5 factorial into 4 factorial, right? So when are you coming from 9 factorial, you will have a point which is equals to ni. That obviously 9 factorial into 9 minus 1, 8 factorial, 7 factorial, 6, sorry, 9 into 8, 7, 6, 5, 4. You have to have a term which is equals to just hi. That
NI.
is hi. That is the term. When you also the hi, we can take the both. Both is correct. You will have
Okay.
that. You will have that term obviously. So that I have written here explicitly. So that is written. So you can see from here, rest of the part is hi factorial. So you can write it ni hi, ni plus hi minus 1 dot 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 ni plus hi minus ni minus 1. Up to this will remain divided by n factorial. Rest of the part will be same as hi factorial. You can do it in terms of n factorial as well. Then it will be hi minus 1. Both you can do. Okay. So that can be done. So if you do it, so what if you simplify it? So it is NiH plus Hi. It is Ni plus Hi minus 1. It will be, if you simplify it, it will be, just look at Hi minus 1. Sorry, plus 1. Just Hi plus 1. Okay. Up to Hi plus 1.
Okay.
Is it clear?
Yes.
So now just open the, what was Hi? Gi minus 1. This was Hi. Put it
Yes.
up to Gi. Correct?
Yes.
So see, each and every term is greater than Gi. So
GI.
it will
Yes.
be Gi to the power ni by n
By
factorial.
NI factorial.
So same way, Bose Einstein will be greater than pi over Gi to the power ni divided by ni factorial. So essentially it means that this Bose Einstein is greater than Maxwell Boltzmann by n factorial. Okay.
Yes.
So in general you can write, so Fermi Dirac, Bose Einstein is greater than Maxwell Boltzmann by n factorial, and Fermi Dirac is less than Maxwell Boltzmann by n factorial. Okay, but this is general. Here no approximation is there. Now we will apply that approximation that Gi is very greater than Ni. If this is the case, then you can, what will be changes? Just look at the equation. If Gi is very greater than Ni,
Then NI will be neglected.
this that means Ni will be neglected, and no, that is okay. But what you say about this inequality? Here, if you ignore this Ni, then it will be just 1 by Ni factorial like this thing, right? But that is,
Yes.
I don't want that. That is okay. That is okay. But I want to say about this inequality sign. That how about this? What you can say about this? In general, the Bose-Einstein is very greater than Maxwell, not very greater than Maxwell Boltzmann by n factorial. Okay, it's correct. But when the Gi is very greater than Ni, then obviously it will be comparable with the Maxwell Boltzmann by n factorial. Okay, it will be greater than. That will not be changed. That will not be changed. But due to this Gi is very greater than Ni, if you impose this condition, then obviously it will be comparable to Maxwell Boltzmann's. That you can see from here. If you do the comparison, that
They
Maxwell
will be
Boltzmann,
equal.
that Bose-Einstein. This is the Bose-Einstein distribution. So when this Gi is very, very greater than Ni, you can think this is as Gi divided by Ni factorial. This is Ni minus Gi. What is this? Ni minus Gi. Sorry, it is Gi minus 1 factorial. What I have written. And that's why it is 8 factorial. Correct. So it is just 1 by Ni factorial. You see? 1 by Ni factorial. Okay. After
Okay.
putting Fermi Dirac, just go. It will be also 1 by Ni factorial.
Yes.
Now Maxwell Boltzmann. What is the Maxwell Boltzmann? Maxwell Boltzmann. It is n factorial divided by Gi to the power Ni divided by.
Ni factorial.
Okay. So this is Gi to the power Ni. So Gi is huge. Just like you can consider 100 to the power 2 like these things. But here you can't ignore that to the power Ni. That you can't ignore. But what you can, but one thing you can,
The Ni in the denominator.
uh, now
The
denominator
Ni
is,
in,
yes, there is 1 by Ni, 1 by Ni factorial. But here is also n factorial. That n factorial is
yes.
also there. But we are considering this divided by n factorial. So just we have to take this. So you can see as Ni is very less. So a huge power thing, if it is to the power some very less thing, so you can write it as 1 by Ni factorial. Do you get it? Ni
Yes.
is less, na? Gi is huge. That's why. Okay. Um, so then you can consider like this. So essentially, this is a general case, and when the Gi is very, very greater than Ni, so it will be comparable to the this. But obviously, it will be slightly more, and it will be slightly less. There, this inequality will be whole because that is a general case. So this is the classical limit. That's why you can see in case of classical limit, this equation you can write for, for Maxwell-Boltzmann particle, for Maxwell-Boltzmann, that capital Q should be Q to the power n. But you see, for classical limit, if you divide it by this n factorial, it will be equivalent to Bose-Einstein or Fermi-Dirac.
Yes.
That's why we divided by n factorial. Although uh, considering indistinguishable particle that are not quantum particle, but if you consider the quantum particle, but you can't prove for quantum particle this relation q to the power n by n factorial. That is not true. That can't be proved. But here you can see you can replace this under that classical limit. Obviously, it will behave like this. So from here, it is evident that under classical limit, a Maxwell-Boltzmann particle, Bose-Einstein or Fermi particle will behave like a classical Maxwell-Boltzmann particle. Okay, so this is called the classical limit.
Okay.
So in next class, I will show two things. First one is that what I have said that Gi is very, very greater than Ni. I have to show this. And after that, I will show some formula from this distribution, Fermi-Dirac distribution. 2, 3 formula to the problem that will take 30 minutes, and 30 minutes I will discuss that density operator. Rest of 1 hour, I will discuss the question that I have said earlier, that you have to collect the question, whether whatever you doubt you have, you can ask me, and that I will discuss in next class. And next class will be next Sunday. Okay. In this week I will going to home, so that's why I will. Okay. So if any doubt, you can ask me. Okay. Now regarding this class or other doubt if you have. From this latter
Question
question,
7 of the last.
yes.
Question 7 of the last assignment.
Question 7 of the last assignment. Okay, let me check. Is the last assignment, right? Means week 12 assignment,
Week 10.
week 10. Okay. Expected population of ground vibrational state at normal temperature is close to. Yes. What should it be?
All are in the ground state.
So it will be 1. Here population means the population distribution. Probability
Why
they
is it
want.
not infinite?
Why it should be infinite? What is
All
the
are in the ground state.
yes? So pi is ni by n.
They has not about probability.
Huh?
They not ask about this.
No. They had asking probability. Probability is
Oh,
also a distribute number. Okay. So these are don't
okay.
confuse this. Ni is the exact number, and pi is also the population, but this is the fractional population or probabilistic population. This is also population
Is the language right?
in the
Language of the question.
yes. Nothing is wrong. Population that you have to understand. You can't. How you can do this? How you can say what will be ni? Is this possible? You don't know capital N, then how you can say? So from this question, you have to understand that population means they want to ask pi.
Okay.
Eventually, they should write fractional population. That is a correct
Yes.
statement. But here you have to understand this. This data is not given to you. So what you can calculate, obviously this. So this is eventually when you can calculate ni, when the capital N is given. Then using this formula, you can calculate this.
Yes.
So fractional population is also a population, na? So that's why I said. Okay.
Okay.
Okay. So let me stop sharing now. Okay. So okay, if you have any doubts, so you can ask. Otherwise, we can stop here today. We'll meet again in the next Sunday. Yes, next Sunday. And I said that what will we discuss.
Okay. Thank you.
Okay. So then, thank you for joining. We'll meet again in the next.
Class only 4 o'clock start.
Yes.
Not only 5.
Hello. Hello. Is there any doubt?
Not outside.
Okay. 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 Then we'll join again.
Thank you, sir.
Okay. So I'm disconnected. You can now leave.